KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with problem number 7, which is exercise problem number 7. Okay, right. See here, see the 7th problem. In a double slit experiment, the angular width of a fringe in a double slit experiment, that is what the Young's double slit experiment, the angular width of a fringe is found to be 0.2 degrees on a screen placed 1 meter away. Placed 1 meter away. Full stop. The wavelength of light used is 600 nanometers. Next, what will be the angular width of a fringe if the entire experimental apparatus is immersed in water? Here, refractive index of water has to be taken 4/3. So, it is a value already given, we don't bother about that. It is what refractive index of water 4/3, right? So, once again I will go through sentence by sentence. You please try to get the imagination regarding the problem, what he is asking or what he is questioning, right? Okay, see this. In a double slit experiment, the angular width of a fringe is found to be 0.2 degrees on a screen placed 1 meters away. Right, full stop. The wavelength of light used is 600 nanometers. It's okay. Obviously, we want the wavelength of light used. Okay, right. What will be the angular width of the fringe if the entire experiment apparatus is immersed in water? Right. Take the refractive index of water to be 4/3. Here the question is the same thing he is asking. So whatever the value they have given, same thing he is asking, but when the entire experimental setup is in water, this is the angular width of a fringe. This is the angular width of a fringe when the experimental setup is in air. What is the refractive index of air? When the same experimental setup will be immersed in water, then what happens to the angular fringe width? Will it change or not? Suppose if it changes, what is that value? That we have to find. Right? Obviously, density of water is different from density of air. So that, in case of Young's double slit experiment, so we are using light rays. When light ray is traveling from air to water, automatically it bends. So that's what we are calling it as refraction, right? So that effect will be there. But he is asking to find, that is what mathematically, what is the changed value? What is the changed value of angular width of a fringe when the entire experimental apparatus is immersed in water? Okay, right. See here, see the solution. Since a fringe of width beta is formed on the screen at a distance capital D from slits, so the angular fringe width would be, this is the formula, that is what theta is, it is the formula for angular fringe width, that is equal to beta by capital D. that is equal to beta by capital D. Theta is equal to beta by capital D. You know already you know the formula for beta, that is what? Fringe width formula, not angular fringe width. Angular fringe width, this is the formula. This is fringe width formula, that is capital D into lambda by small d. You know already capital D is here, so these two will get cancelled. The output will be lambda by d. So angular fringe width in terms of wavelength of light used and distance between the two slits is lambda by d. You know when theta is equal to lambda by d, mathematically you can write it as d is equal to lambda by theta. D is equal to lambda by theta. Okay, right. When d is equal to lambda by theta, see here next one. That is what? If the wavelength in water be lambda, if the wavelength in water be lambda dash, you know this is dash ma. If the wavelength in water be lambda dash and the angular fringe width be theta, angular fringe width be theta, right? Then you know, sorry, this is what? Theta dash ma. It is lambda dash, it is theta dash, right? See here. So because in air we are assuming as lambda and theta, no. Here we are assuming as lambda dash and theta dash. Okay. See. So if the wavelength in water be lambda dash and the angular fringe width be theta dash, then d is equal to lambda dash by theta dash. But one thing you keep in mind, whether the experimental setup is in water or whether the experimental setup is in air, wherever the medium, distance between the two slits will not change. Am I right? When the experimental setup is in air, when the experimental setup is in water, distance between the two slits will not change. Obviously, it is the distance between the two slits and there will be no change because it is a matter of physical, right? So this medium, that is what, whatever it may be, either water or some other medium, which will not change the distance between the two slits. That's why you can write here also small d, here also small d, that is equal to lambda dash by theta dash. Therefore, you know, here it is d is equal to lambda by theta, here it is what? D is equal to lambda dash by theta dash. Therefore, lambda by theta is equal to lambda dash by theta dash. Lambda by theta is equal to lambda dash by theta dash, right? So it is what we want to write a theta dash as a subject because that we need to find. That we are going to find. Okay, see here. So theta dash is equal to, it is what? Lambda dash into theta by lambda. Is a mathematical I am writing. So how we are getting this one? That is concept. But from this step I am writing this one, means it is purely mathematical. You know this is what? Lambda dash into theta by lambda, and here lambda dash you can write it as lambda by mu. Lambda by mu. Okay, that is what? Lambda dash, that is what? Wavelength of light in water we are writing. Wavelength of light in water we are writing in terms of wavelength of light in air and refractive index. Okay, right, divided by lambda into theta. Okay, so here if you observe carefully, these two will get cancelled. That is what? Lambda will get cancelled, and then it is the final answer will be theta by mu. Right? So theta already you know, that is what? 0.2 degrees given, and then mu is 4 by 3. So the final answer will be 0.15 degrees. 0.15 degrees. Okay, so 0.15 degrees is the angular fringe width when the entire experimental setup kept in water or immersed in water. So can you tell me whether it is increased or decreased? Generally I am asking, it is not a part of question, but for our estimation, because sometimes in our competitive exams like NEET and mains, simply they will keep, they will ask, what they will ask? Suppose if the Young's double slit experiment immersed in water, then what happens to the angular fringe width when compared to the air medium? So what is the answer? What are the options? Increases, decreases, remains the same? We cannot say. So finally, what is the answer here? Decreases, right? So when you are shifting, when you are taking the entire Young's double slit experimental setup from air to water, then the angular fringe width will be decreased. That is the thing we have to keep in mind to answer theoretical based questions, right? Next question, it is what question number 8. What is Brewster's angle for air to glass transition? What is Brewster's angle for air to glass transition? The bracket mu for glass is 1.5. Mu for glass is 1.5. Okay, right. You know, this formula is very, very important. If you see the previous year question papers, right? So we had this formula, we had problems based on this formula many times, right? That's why this formula is important, and it is very simple. That is what mu is equal to tan IP. Mu is equal to tan IP. That is the only formula, right? So here they have given refractive index now. That is what 1.5. So by Brewster's law, tan IP is equal to mu is equal to 1.5. So mu is the refractive index for glass, right? So he is asking what is Brewster's angle. So we have to find IP, right? So IP is equal to tan inverse of 1.5. Tan inverse of 1.5, right? So tan inverse of 1.5 means what? That is equal to 56.3 degrees. 56.3 degrees. That is what Brewster's angle. 56.3 degrees. Okay, right. That only he is asking now. He is asking what is the Brewster's angle. That is 56.3 degrees. Next, ninth problem here. Right, next problem. See this. A light of wavelength 5000 angstrom unit falls on a plane reflecting surface. Light of wavelength 5000 angstrom unit falls on a plane reflecting surface. Try to imagine, Try to imagine what is a plane reflecting surface, right? A light of wavelength 5000 angstrom unit falls on a plane reflecting surface, full stop. What are the wavelength and frequency of the reflected light? Generally, you know, when a light is going to incident on a plane reflecting surface, what will happen? It will reflect into the same medium. That is called as natural phenomena, which is reflection. Right? There itself, you know, what is meant by reflection and what are the laws of reflection, So those two things we need to solve this problem, right? The phenomena in which incident light bounces back into the same medium. Phenomena in which incident light bounces back into the same medium is simply termed as reflection. It is naturally it happens. Just we are calling it as reflection because of sending back of light into the same medium. Okay, right. Next, what are the laws of reflection? First law is angle of incidence is equal to angle of reflection, right? Second law is incident ray, normal, reflected ray. Incident ray, normal, reflected ray lie in the same plane, right? So three things. What is reflection and what are the laws of reflection, right? The phenomena in which or phenomena due to which incident light bounces back into the same medium, right? Incident light bounces back into the same medium from the point of incidence. So what is point of incidence? On a plane surface or on a reflected surface, the point where incident light meets is called as point of incidence. Point of incidence. So from the point of incidence, again the light sends back into the same medium. So this phenomena is called as reflection or reflection of light. Reflection of light. Okay, right. So here itself, what is normal, what is angle of incidence, what is angle of reflection, right? And that and all we discussed in the chapter of ray optics when we were in a discussion about the topic of reflection. Okay, right. And next two important things are laws. So first one is angle of incidence is equal to angle of reflection. Second one is incident ray, normal and reflected ray lie in the same plane. Lie in the same plane. Okay, that is. See here. Next, we are going to see the solution. The speed of light is fixed. The speed of light is fixed in a given medium and frequency of light does not change. The speed of light is fixed in a given medium and frequency of light doesn't change during its reflection, right? See, the speed of light is fixed in a given medium and frequency of light doesn't change during its reflection from a surface. Consequently, the wavelength should also remain unchanged because C is equal to n lambda. C is equal to n lambda or C is equal to nu lambda. C is equal to nu lambda, right? So when C is equal to nu lambda, what is nu? Nu is equal to C by lambda. C by lambda. Here C is constant. That is what the speed of light in one particular medium is constant, and nu is also constant. The same type of situation we got in our previous class also. So frequency also remains frequency also remains constant. That is what doesn't change. Why? Because frequency depends upon the source of light. Frequency depends upon the source of light, not on the medium. That's why frequency is constant, and in one particular medium, speed of light is constant because frequency is constant and wavelength will not change. When wavelength changes, when light travels from one optical medium to another optical medium. So this is the information I explained you clearly when we discussed about the topic refraction, because their light is going to propagate from one optical medium to another optical medium in our that is previous chapter. Previous chapter means not wave optics in case of ray optics, right? So in ray optics we discussed clearly regarding the refraction. When a light propagates from one medium to another medium, what happens to the wavelength, what happens to the frequency, what happens to the speed. Okay, that is, see here, the speed of light is fixed in a given medium and frequency of light doesn't change during its reflection from a surface. Consequently, from a surface consequently means from that you can also say the wavelength should also remain unchanged, because wavelength is the ratio of the speed of light in a medium to the wavelength. Wavelength is the ratio of speed of light in a medium to the frequency, because C is equal to nu lambda, no? C is equal to nu lambda. Okay, right. Next step. From this we are writing speed of reflected light is equal to speed of light in air. Okay, because suppose it is a reflected surface means it is what incident light and it is what reflected light. Okay, it is what incident light and it is what reflected light. Okay, right. So speed of reflected light is equal to speed of light in air. So you know that constant, it is what generally C is equal to 3 into 10 to the power of 8 meters per second. From this you know speed is equal to n lambda, no? Speed is equal to n lambda or nu lambda, right? Speed is equal to nu lambda. So here also nu lambda, here also nu lambda. It is what nu will get cancelled because frequency remains constant or frequency doesn't change. Frequency doesn't change, right? So here wavelength of reflected light is equal to wavelength of incident light. Wavelength of incident light, right? When this is correct, you can write this one also. Next, lambda is equal to 5000 angstrom unit. That is the value they have given. See, light of wavelength 5000 angstrom unit falls on a plane reflecting surface. So what does it mean? Here, it is the wavelength of incident light. Wavelength of incident light. Okay. So lambda is equal to 5000 angstrom unit, that is equal to 5 into 10 to the power of minus 7 meters. So he is converting angstrom unit into meters. That's why here we are getting 5 into 10 to the power of minus 7 meters. Next, frequency of reflected light. Frequency of reflected light. Nu is equal to C by lambda. We want to find frequency of reflected light. That is what nu is equal to C by lambda. That is 6 into 10 to the power of 14 hertz. We have to substitute the values and then finally we will get it as. But if you see the question, what he is expecting from us, what are the wavelength and frequency of reflected light, right? So we found wavelength of reflected light. It is 5 into 10 to the power of minus 7 meters, and we also found that is what the frequency of reflected light by using the formula nu is equal to C by lambda, that is 3 into 10 to the power of 8 divided by 5 into 10 to the power of minus 7, that is equal to 6 into 10 to the power of 14 hertz. 6 into 10 to the power of 14 hertz. It is frequency of the reflected lights. Frequency of the reflected lights. Okay, right. Next, by the laws of reflection, you know, angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection. It is first law of reflection. So in the same class I told you before 2 minutes what are the laws of reflection. So the first law of reflection is angle of incidence is equal to angle of reflection, and the second law of reflection is incident ray, normal and reflected ray. Incident ray, normal and reflected ray lie in the same plane. It is a conceptual thing, ma. For example, it is a plane reflecting surface means if it is the incident ray, this is the reflected ray. It is the normal, right? So these three things, incident ray, normal and reflected ray should lie in the same plane. Okay, right. Okay, anyhow here we need first law of reflection. So it is angle I is equal to angle R. And you know, for what angle of incidence is the reflected ray normal to the incident ray? So he is asking what is the angle of incidence when the angle of incidence for angle of refraction, angle of incidence for angle of reflection is equal to 90 degrees, right? So when these two are equal to 90 degrees, already you know that angle of I is equal to angle of R. So you can say that angle of I became 45 degrees. So 45 degrees is the angle of incidence. Okay, right. Next problem, it is problem number 10. See here. Estimate the distance for which ray optics is a good approximation for an aperture of 4 millimeters and wavelength 400 nanometers. Once again, estimate the distance for which ray optics is a good approximation for an aperture of 4 millimeters and wavelength 400 nanometers. Wavelength 400 nanometers, right? For these two values, this is what aperture value and this is what wavelength 400 nanometers. For these two values we have to estimate the distance. Okay, see here. First you have to write the given values. A is equal to 4 millimeters, that is equal to 4 into 10 to the power of minus 3 meter. 4 into 10 to the power of minus 3 meter, and lambda is equal to 400 nanometers. Lambda is equal to 400 nanometers, that is equal to 4 into 10 to the power of minus 7 meter. 4 into 10 to the power of minus 7 meters, right? So wavelength lambda is equal to 4 into 10 to the power of minus 7 meters, right? We know that this is the formula df, that is what distance for which the ray optics is a good approximation. df is equal to a square by lambda. See here ma, a square by lambda. So a value already given, that is what 4 into 10 to the power of minus 3 whole square, square is there, divided by, this is lambda value is 4 into 10 to the power of minus 7. So because of the mathematical calculation, you do the calculation, then you will get it as 40 meters. 40 meters is the distance for which ray optics is a good approximation. That only he is saying here. Thus the ray optics is valid up to a distance of 40 meters from the aperture. So this problem you should not see like a problem. You have to keep in mind. See, the validity of ray optics we are calculating. You know, with this aperture and with this incident light wavelength, right? With this aperture and with this incident light wavelength, right? We have to find the distance. It is 40 meters. Up to 40 meters, the light ray behaves. That is what ray optics is valid. So light propagates in the form of a ray. After that, the validity of wave optics starts, right? So for this value of aperture and for this value of incident light wavelength, and it is what 40 meters is the distance. Up to that, ray optics is valid. Okay, right. So in this class we discussed 4 problems. In first problem we calculated the angular fringe width when the experimental setup immersed in water. So obviously it decreases. That value also we calculated as 0.15 degrees based on the given data. In second problem we calculated Brewster's angle. By knowing refractive index, we found or we calculated Brewster's angle. It was 56.3 degrees. The ninth problem here we found, that is what wavelength and frequency of reflected light, and afterwards we also found angle of incidence when the angle of reflected ray normal to the incident ray. That is what. Okay. So based on the given situation, according to the situation, we found angle of incidence as 45 degrees, right? In the last problem, again we are going to see, we have seen the validity of ray optics. You know very well the validity of ray optics belongs to these two, that is what aperture and wavelength. Okay, and based on for these two values, the validity of ray optics is up to distance of 40 meters, up to a distance of 40 meters. Okay, right. So in our next class we will continue with next exercise problems. Thank you.